Another approach to studying the history of our universe, measuring the cosmological parameters, is to do what we discussed at the beginning. You could try to measure the deviations from the linear redshift distance relation that is the Hubble law. And remember, the deviations are sensitive to the history of the universe. And so how would you do that? Well, you can measure the redshift to some object. You need to measure the distance to the same object. How do you measure the distance to things? We're good at that by now. To measure the distance to something, you need to know its luminosity, measure its brightness, and use B equals L over 4 pi d squared. You have to remember to use luminosity distance corrected for redshift, but you're measuring the redshift. What you need is an object you can see at great distance, which therefore has to be very luminous, and whose luminosity you know. We made a big deal about such objects. Type 1a supernovae, the explosions of white dwarfs as they approach the Chandrasekhar limit because of accretion from a binary partner, form precisely very luminous standard candles. And so in the early years of this century and the last years of the last, two groups set out to use type 1a supernovae as standard candles, measure their brightness, know their luminosity, compute the luminosity distance, measure the redshift of their absorption lines of silicon and so on, and figure out the redshift, and figure out the corrections to the Hubble law at large redshifts. What does this mean? Well, what they were looking for is a measurement of the deceleration parameter. Remember, we expect expansion to be slowed down by gravitational attraction, and so we expect that in the past, expansion was more rapid than it is now. Convert that to what you expect for the redshift. You expect the redshifts of distant galaxies to be larger than predicted by the Hubble law. We saw that for the positive curvature universe in my dust universe model when we played around with those examples. And so here's the data from which they can learn this. You see that the data is quite noisy. You see that they have made amazing achievements. They have measured type 1a supernovae up to z equals 1. That's a distance of about 13.8 billion light years away. That's a large distance. And while the data is noisy, they managed to draw a conclusion, and both groups drew the same conclusion, and the surprising conclusion was that the deceleration parameter is negative. In other words, we live in an era in which expansion is accelerating, which means that since all kinds, both dust and radiation, all kinds of normal matter, contribute to deceleration, the only expression in our equations that drives acceleration is the cosmological term with its weird negative pressure, and for that reason, we think that this is an almost direct measurement of the presence of a cosmological term. You notice here that the deviations they are measuring from the Hubble law and the distinction they can make based on this data requires some analysis, but if you assume that there is no vacuum energy, this would be your predicted Hubble relation corrections, and clearly this is excluded from what they have measured. And so they actually have a precise measurement. Here's a historical view putting the supernovae at the time at which they actually exploded, and this is the selected pattern of expansion that we're seeing, and you see that what they are measuring is sort of this very slight positive curvature over here. As we said, we are in the process of turning over from slowing matter-dominated or dust-dominated expansion, like t to the 2/3, into an exponential. We're in the transition region today, and we are measuring this slight bit of positive curvature. So another constraint on cosmological parameters, and between that and the previous one, let's see what we have.